Good morning, everybody. Does anybody need the flash drives? Or are you all rolling on Google Drive now? You want one? So I hope you all had a good night last night. You need one? Yeah. Do you know what? There's materials all the way through Friday in here. There's just one presentation missing from Friday that Pat's going to bring. So, the Google Drive has been updated so that the Wednesday and Thursday files should all be there. And Ashley has an announcement to make. Okay. On the drive. Okay. Okay, so sometime around lunch, if you're using the flash drive, we'll just get you the new version of the one after lunch, okay? So we didn't get through one of the lectures from yesterday. We always plan too much for this because we're so excited. We're like, let's see how much we can pack in. So we are going to start with yesterday's 4 o'clock lecture, and we are going to skip trend today. And we will do that as a post-training webinar, trend analysis, which I'm really hoping to employ Deb Rosenberg's help. She usually is one of the trainers here. She's a great teacher. She's gotten teaching awards, and she wasn't able to come this year. She's retired now and kind of doing less and less, and but she was interested in doing post-training webinars. So I think that her and I will probably do trend together as a post-training webinar because we just can't fit as much as we wanted to on site. So we'll start with the 4 o'clock lecture from yesterday then. And before we do begin, do we have any questions? Okay. Well, we'll just dive right into regression modeling then. Okay, that sounds good. Great. All right. So I did want to I just talked about Deb, actually. Do I need to, did I do it the wrong way? There it goes, okay. So I wanted to acknowledge Deb because she's been an amazing mentor of mine over time, and she's trained in this course for a really long time. And so I've used a lot of her training materials and built off of them. But the coolest thing is that she created this PowerPoint slide template. Look, it has the planning cycle and a regression equation underneath. She's really good at like the graphics and everything like that. So it's been really fun to use this. All right, so the goals for this session are that we're just going to briefly review contingency table analysis from what we talked about on the webinar. And then we're really going to get grounded in 3 types of regression models. 2 multiplicative models, which are the logistic and log binomial, and an additive model, which is the binomial. So from the multiplicative models, from logistic, we're going to estimate odds ratios. From log binomial, risk ratios or prevalence rate ratios, depending on the design and how the outcome was captured. And binomial, from the additive model, we're going to be estimating risk or prevalence differences. And so that's what Ashley was kind of highlighting yesterday, or talking about what we'd say. We're really going to learn how to do regression modeling with risk differences today. We're going to discuss what adjustment means in a multivariable model, and then interpret results from multivariable models. So here's just a list of all the steps that need to come before regression modeling. I kind of drilled this in on the webinar, but I'm a true believer that you need to be looking at your data in tables all the way up through stratified analysis to get intimate with it. You know, you really want to understand what's going on. And the regression model is a bit of a black box. And I know a lot of analysts start right at the regression model. And if you do that, you're making a lot of assumptions about your data, about the structure of your data, about the, you know, whether the data are sparse or not. You don't know that going right into a regression model. So I do think that all these steps are very, very important before you get there. And then also, like we talked about yesterday, you know, constructing your table shells, thinking about potential charts or graphs, thinking about narrative, even before you get into the heavy-duty analysis so that you really focus your analysis on what your end product's going to be. And the reason we moved to regression modeling then from contingency table analysis is that it handles more variables efficiently. So with contingency table analysis, you get to a limit of how many 2x2 tables you can have, right? How many times you can stratify. So, and you might want to include variables in your model that are continuous, that are discrete, you know, categorical. So you have more flexibility in a model to do that and to do that with a lot of variables. And then also you don't really need to identify this primary independent variable because everything on the right side, I'm going to be talking about the right side and the left side of the model. The right side is where all the independent variables go. Everything on that side of the model, they're going to be mutually adjusted for each other. So when you're using a software program and putting a model in, they don't know what your main variable of interest is. They're all treated the same on the right side of the model. But that allows you more flexibility, too, to kind of interpret the results from the model how you need to and how it's best going to inform action. Okay, so this is a typical structure for a linear model. Where and this is what I was talking about, the left side of the equation is your outcome or your dependent variable. And then you have your independent variables on the right side of the equation. And here the notation is this is from 1 to k independent variables. So you may have, you know, depending on your sample size, you could have, you could support several independent variables on the right side of the model. And then you have that beta coefficient to describe the relationship between those x's and the outcome. All right, and what I skipped over kind of was the intercept here, right? The intercept is going to be where the regression line crosses the y-axis, and in this case, in the case of a multivariable model, where all of the x's equal 0, right? Okay, and then your associated with your outcome is going to be your error term. And so this equation can be generalized really to any linear model. And what differentiates each model is the structure of the outcome variable and then the corresponding structure of the error terms. So this may be the model that you're most, you know, familiar with from statistics classes. It's just a pure linear model, right? So now in this case where the outcome, well, I guess this is still generalized to any model. There's that linear relationship. This is just depicting that linear relationship with the intercept being where the regression line crosses the y-axis. And then you have the relationship, the beta is the slope. The points are the observed values. And the error is how far away those observed values are from the predicted slope. And here's the traditional normal linear regression model where your y, your dependent variable, is continuous and normally distributed, and you're actually modeling the mean of y. The y values are independent of each other, and the errors are independent and normally distributed. And the linear relationship we're modeling here is the mean of y with all of the x's. So if you think about a line, for a multivariable model, it's like a line in multi-dimensional space. It's kind of hard to think about, right? If it was just a simple model where we're predicting the mean of y equals beta 0 plus beta 1x, then you're looking at just that, you know, that two-dimensional straight line relationship there. But with the multivariable model, it's in multi-dimensional space. So that's the last time we're going to look at a normal linear regression model for the whole week, because as epidemiologists, we're hardly ever and especially as MCH epidemiologists, I feel like, how many outcome variables do we have that are truly continuous? normally distributed, meet all of those assumptions, right, we're often looking at either dichotomous or categorical outcome variables. So we're going to just use our knowledge of that regular linear regression model to build and expand upon that. So when our outcome variable is not continuous and normally distributed, we can write the model in the same way, but we have to transform the outcome in order to make that straight line relationship. And that's true for the multiplicative models. So our errors are not going to be normally distributed if you have a dichotomous variable as your outcome, because the variance of x is not going to be constant like it is with a continuous outcome variable. Because if we're modeling a proportion, so a prevalence or a risk, the variance is p times 1 minus p. You can see that that's not constant over levels of p. And the same is for a rate, because the variance of a rate is the same as the rate. So it's going to change with the rate. And then, so that expected value, the proportion of rate, is not linearly related to x, so we need to transform it. So this is kind of just a general diagram of how an x value tends to be related to the proportion of an outcome. You see this nonlinear relationship. So I like to think about this when we transform the outcome variable, it's like pulling that S line into a straight line. So we need to do something to transform the dependent variable to make that a straight line relationship so we can use that linear regression model. And we do that by using a link function. The link function transforms the variable. And so some common link functions are identity, which is untransformed. So you would use that in a linear regression model, and you'll see we're going to also use that in a binomial regression model when we're modeling risk differences. There's the natural log transformation, which we're going to use in log binomial regression. There's the logit, which is the natural log of the odds. This is actually the natural log of the proportion itself, and then we have the natural log of the odds. And then there's two other link functions that we won't talk about this week, but it's cumulative logit and generalized logit. And those are useful if you have an ordinal or a nominal outcome variable, so beyond 2 categories. And that's, one thing I wanted to say is that we do want to offer several post-training webinars to kind of keep up the skills, but also cover some other topics. And that's a potential for another topic, is thinking about cumulative or generalized logit, if that's useful in your work. But we're probably going to have a series of topics that we'll have you kind of vote on and be able to provide for you, every couple months after the training. Just keep that in mind. And if you guys have any other suggestions about topics you'd like beyond the on-site training that we could add to that list for voting, just let us know sometime during the week or email us afterwards, okay? Trend will now be one of them too. Okay. All right, so with these transforms now, this is the natural log of, this is the logit transform because it's the natural log of the odds. Now, if this is your outcome variable, the right side of the equation looks exactly the same as it would in a linear regression model, except the errors are going to be distributed binomially, because we have this proportion here. So we have a dichotomous variable. We're modeling the proportion over 1 minus the proportion, which is the odds, and taking the natural log of that. And once we transform that, we have, again, a straight line relationship. And now what we're predicting, these beta values are going to be the natural log of the odds of the outcome, okay? They're going to be, when you combine the beta coefficients, they're for predicted values, they're going to be the natural log of the odds of the outcome. In log binomial regression, we're taking the natural log of the proportion or of the rate. And if we take the proportion, it's a binomially distributed errors. And for rates, the errors are distributed with a Poisson function, okay? A Poisson distribution. And for binomial regression, actually, we're going to use the identity link. So we're modeling proportions directly in a straight line relationship. But what differentiates this from a regular linear model is that the errors are distributed binomially. And so you see the link function is identity, but the distribution is binomial. If this was just a linear regression model with a continuous outcome, the distribution would be normal, okay? So any questions so far on kind of the basics? I promise you won't see hardly any more like Greek after this because I don't like it much myself. But I just wanted to start with this foundation of how we're transforming the outcome to get this linear regression model. Ellie? Identity just means untransformed. It means, identity just as itself. It's untransformed. So we're actually modeling for the rate, but what the regression equation looks like, it's for each individual, it's going to be a 1 or 0 value, right? But the model itself is predicting the rate for the whole, or for the whole sample. Does that make sense? Yes. Mm-hmm. So for a normal regression, this would be a mean of the outcome equals, this linear regression equation. For this, it's the proportion or the rate. It's that aggregate of the whole sample. But this is based on individual level data, though, where you have 1s and 0s for the outcome. Any other questions? Okay, well, let's go on with some examples then. So here's just a summary. These are 4 different regression model types. So in the black, it says the regression model types and the link and the error distribution. In the red is the measure of occurrence you can get from that model. And in the blue is the measure of association. So this is just kind of a nice little summary. You might want to tag it, just to remind yourself. So in a normal linear regression, we're looking at measure of occurrence as means, and our measure of association is the difference between means, right? In an additive model, and so here's the binomial model, it's the identity link, the binomial error distribution. We're looking at the log probability, which is either a prevalence or a risk, depending on how we've collected our outcome variable, right? Is it a prevalence or an incidence? And we're looking at risk, we're looking at risk or prevalence differences here as our measure of association. In logistic regression, we're modeling the log odds, and we're looking at differences between log odds. And usually we don't report that the measure of association is a difference in log odds, right? We exponentiate to get it back on the odds ratio scale, right? So that's the thing with these 2 multiplicative models down here. Because we transformed the outcome variable, we need to do something to transform it back when we're interpreting the results, right? So we're going to use exponentiation for both of them. This, for logistic regression, we're going to exponentiate to get odds ratios because exponentiating is taking the inverse of the natural log. So we're getting the odds ratios, and for the linear multiplicative model, which is log binomial model, we're modeling the log probabilities, the prevalence or risks, and then exponentiating and get risk or prevalence ratios. Okay. And then just generally, the confidence intervals, this is very general, and you'll see it for each of the models, but the confidence intervals for our beta coefficients, which are going to, you'll see they're going to be our measures of association, is that it's beta times the difference, and if you're just working with a dichotomous variable, the difference is going to be, if it's 1 minus 0, it's just going to be 1 times the beta. And then plus or minus the critical value, which you were usually doing 95% confidence intervals, so does anybody remember what the 1 minus 0.05 over 2 is? 1.96, that's one of those ones that's drilled in your head, right? So 1.96 times the standard error of the beta then. So when the regression model uses maximum likelihood estimation to estimate those betas, you're also going to get a standard error with each beta. And then the confidence intervals are computed like this. And so this difference, it could be if you have a continuous variable, you're comparing age 20 to 40, then the difference would be 20, the 40 minus 20, right? So that's just the only difference depending on the level of measurement of your independent variable. And then the test statistics, you're going to get a Wald chi-square test for all these, and it follows that same kind of form of the observed minus the expected beta over the standard error of the observed beta. I like that the software calculates this all for you, but it's just a good reminder of how that was calculated, right? So I'm going to focus very little on logistic regression because I figure that you probably all have a pretty good foundation in it. And, Ashley talked about all the problems with the odds ratio yesterday, so we're really trying to move away from that since we have some software solutions now to model prevalence rate ratios, risk differences. But I do want to say that I think probably the gold standard method right now for estimating relative risks and risk differences is actually from a logistic regression model and using marginals to actually compute the relative risk and the risk difference from a logistic regression model. And the reason for that is this is very mathematically stable model. So if you work with Stata, I think Ashley's going to show some code later that shows how to actually produce relative risks and risk differences from this. It's more difficult in SAS, and I think the majority of you are SAS users. There is a macro, and I have a link for it at the end of this. But I'm going to basically focus on the log binomial and the binomial regression models here as ways of getting relative risk and risk differences. I just want you to know that I think the field is moving a little bit more towards using logistic regression and transforming what we get out of logistic regression for risk ratios and risk differences. So we can talk to you more about that kind of on an individual basis too. Okay, so quickly with logistic regression, when the outcome is a proportion with a logistic transformation, these predicted values are log odds. And so when I say predicted values, I mean we're actually solving, we're actually plugging into the regression equation. So here the natural log the natural log of the outcome for where x equals value a. So if we think about this as a dichotomous variable that's coded 1 and 0, value a is 1, value b is 0, we're predicting the natural log of the odds of the outcome for value a, okay? So you would add the intercept, you would just plug in the values to the regression equation, the intercept to the beta 1, and times that value a. And that would give you the natural log of the odds of this outcome. And you could exponentiate that and get an odds. We usually don't report just plain odds, right? You get the odds for value A, the odds for value B. You could take the ratio of those and have an odds ratio, right? And here if value B, this is why we code our dichotomous variables, 1s and 0s, because it's really convenient if the 0 just drops out. And so the natural log of the odds of the outcome where x equals value b, if it's 0, it just reduces to the intercept. Okay. So now for the measure of association, actually how to compute an odds ratio, you take the natural log, you're really looking for the difference in the log odds between those two values. So the difference in the log odds of the outcome between x equals value a and x equals value b. And if you plug in what we just saw for the predicted values, you can see that this reduces to beta 1 times value a minus value b. So if we have a dichotomous variable, beta 1 is actually the log odds ratio for that x value, okay? And then if we exponentiate it, we get the odds ratio, okay? So just a little bit of kind of plug and chug in the equation to see how we can convert the betas to be our measures of association. And this is in a very simple model with just one independent variable, an x variable. And now if this was a continuous variable, and even on the right side of the equation, I feel like whenever I'm trying to come up with examples for MCH with continuous variables, we don't have a lot that really truly act in a continuous way, because we have maternal age, right? But we have a U-shaped relationship usually where risk is higher, of adverse birth outcomes at lower ages and at higher ages. So we don't ever want to model that as a continuous variable because it doesn't have that linear relationship with the outcome. So we don't have a lot of these continuous variables, but if you are in that situation, you could have your beta 1, you're just going to multiply by the difference between the values that you're interested in. So you'd have to choose, are you looking for every 10-year increase in age, and what's the odds ratio for that? Then you would multiply the beta by 10 and then exponentiate it to get an odds ratio. Any questions, or is this sounding familiar, kind of like riding a bike, for those of you who don't use it a lot? Okay. Okay, great. So just an empirical example, because this is where I think it makes a lot more sense. So I don't know if you remember from the webinar, but I was looking at just a dichotomous association. We're back to the conceptual model we were talking about, the data from the conceptual model from yesterday, where this is just looking at women served by MCO-A versus all the other MCOs. We have 4 MCOs here. We're just looking at A versus everybody else for the simple 2x2 table, and then looking at postpartum visit rates. And do they differ between MCO-A and other MCOs? So here you have the postpartum visit rate for those served by MCO-A is 41%. And for other MCOs is 57%. And remember, this is according to the HEDIS measure, so it was a routine postpartum visit between 21 and 56 days postpartum. So in order to get an odds ratio from that, can anybody tell me how the 0.53 odds ratio was computed? Just in general, I mean. Okay, so everybody remembers A times D over B times C, right? Which is actually, it's actually a simplification of the 41% divided by the 59% divided by 57% divided by the 43%, right? Because the odds is P over 1 minus P. But that simplifies to A times D over B times C, right? Remember that one's another one that's drilled into your head with 1.96, right? So if you computed that, you would get the 0.53 odds ratio. And does anybody want to interpret that for me? Has the coffee kicked in yet? Yes.
I can try. So, sounds like going to MCOA is, if you go to MCOA, you have half the odds of having a postpartum visit compared to if you went to any of the other MCOs.
Good. So you correctly talked about differences in odds, right? So those served by MCOA have half the odds of receiving a postpartum visit compared to their counterparts that were served by other MCOs, right? It's not half the likelihood. It's not a 47% decreased likelihood, right? Because this is one of these very common outcomes. So our odds ratio, wait till you see how much it's overestimating the relative risk. So we do want to be clear, if you are reporting odds ratios, just to be very clear that it's a difference in odds, okay? So how that relates, so I went back to, you notice I went back to the 2x2 contingency table. I just wanted to show you that this is, in a simple logistic regression model, you can get exactly the same thing. And so I have included some SAS codes in these slides, but we will be posting later the Stata equivalent if you're a Stata user. So I needed help doing that because I'm not so fluent yet in Stata. I'm getting there, but so we'll be posting that for you in case you don't use SAS. But just to kind of walk through, this is really simple code for logistic because SAS actually, I mean, it's been such a popular regression equation that they did a procedure just for logistic regression. So it's proc logistic and you put in your data set. And so here's the model statement, and it's just a very simple model. These are both dichotomous 1-0 variables where postpartum visit equals MCOA. And just one thing, I have formatted these variables, and I've tricked SAS by formatting it into modeling this the way that I wanted to. Because typically with a 1-0 variable, it's going to model 0 versus 1. Now, I've formatted postpartum visits so that it's going to use, SAS by default uses the formatted value, and I've formatted it as yes with a space in front of yes versus no, so that I've gotten it to go the right direction. Many of you may have used a descending statement to flip around a 0-1 variable if you don't have it formatted, so I just wanted to point that out. And if you're interested in kind of those tricks, they were in the appendix of the webinar. I didn't want to go through a lot of detail about that, but if you want to go back to the appendix, from the webinar, I talk about kind of it also works for setting up your 2x2 table correctly. You see these formatted values here. Oh, I'm sorry, I didn't use S and O. I actually used postpartum visit, no postpartum visit. But I put a space in front of this P so that it would come before N, right? So that I could get my A, B, C, D cells exactly how I wanted them, okay? So go back to the webinar appendix, and if it doesn't make sense, please email me. I'm like the master of formats now, and it takes a little extra time. I'm the Jedi master, is that what Bill was saying yesterday? It takes a little extra time to do it, but if you do it, all of your data are set up correctly so that you make sure you're modeling things in the direction you want to, and your 2x2 tables show up how you want to too. But you still have underlying 1-0 variables. Now I've noticed, I can't remember if they still do it this way, but like in params, it used to be everything was coded 1-2 for yes, no. Is it still like that? Oh, that drove me nuts. And so if you don't want to format, it actually works for a 2x2 table to have your value for no being 2 because they go in the right order, But once you get to regression modeling, it's so convenient to have the 1s and 0s because so many things drop out with the 0s. So I always recode params variables, all the 2s to 0s, but then I format them so that they come out right. So that was super techy, but if you have questions about that, either on site or afterwards, just email me. I can help out with that. Okay, so back to the actual regression equation. We always have this model statement where outcome equals the independent variable. And so we get a maximum likelihood estimation is used to iteratively decide what this beta coefficient is to describe that linear relationship between the natural log of the odds of getting a postpartum visit and being an MCOA. And from that regression equation, we got a beta 0. This is our intercept of 0.2672. And our beta 1 for MCOA is negative 0.6308. So now, like I said, because this is the natural log of the odds ratio, or the natural log of the difference in odds, you can think of it both ways, between MCOA and other MCOs, you exponentiate that and you see you get that exact same 0.53 that we got from the 2x2 table. This is A times D over B times C from the 2x2 table. Okay, so for a simple logistic regression model, you can see how it directly relates to contingency table analysis. And we already talked about the interpretation. Okay, so enough on logistic. We're going to talk about log binomial now. But once you learn kind of that general process, it works for all the regression models. So once you kind of learn the language and that of these linear regression models, you just have to remember how this is transformed and then how you need to transform it back to interpret the results. And so here's our log binomial model, another multiplicative model here. We're taking the natural log of the probability of the outcome. So this is the prevalence or the risk. And this is, again, a dichotomous. We're coding it 1-0 outcome. And that is a linear relationship with the independent variables with that transformation. So again, the link is log, the dist is binomial. That's why we call it a log binomial model. And in SAS, we use this really flexible procedure called GenMod. And GenMod can run a lot of different kinds of models. You can run a logistic model in GenMod. We usually don't because ProcLogistic is, there's extra options and stuff that's tailored for that. But you can also run a number of different models, but you actually have to specify then what is the link you want, what is the distribution you want. So you could run this and say link equals logit, dist equals bind, and that's what's going on in the background by default in ProcLogistic, right? You don't have to actually specify it because there's a special proc for it. In here you have to specify what your link is and what your distribution is. So that's our log binomial model. The model statement looks the same, outcomes equals exposure, and then we're not going to, this doesn't apply for this particular example here where we just have two dichotomies, but I'm going to talk about dummy variables in a little bit, and the class statement is useful if you want to create dummy variables for a categorical variable with more than two categories. Okay, so we've been over this before, so I'm not even going to talk about it, but the predictive values, are the log probability, and the measures of association are going to be prevalence rate ratios or risk ratios. And as you can see, the right side of the equation, it looks exactly the same as logistic. So once you learn kind of how this works, that on the left, if you're comparing x equals 1 to x equals 0, you want to look at what's the natural log of the probability of the outcome among those with the exposure and among those without the exposure, and take the difference of those. And if you plug in the right side of the equation for each of those, you can see that this reduces to just beta 1 times 1. So the beta 1 is going to be the natural log of the prevalence rate ratio, or the relative risk, okay? And if you exponentiate that beta 1, that's going to be the relative risk of the prevalence rate ratio, okay? So one thing, I don't know if you guys remember, and this is just one of these mathematical rules that you just got to remember and you take for granted, but the exponentiation of the difference of two measures is equivalent to the exponentiation of that measure divided by the exponentiation of the other measure. You guys remember that? So that's where we get this ratio measure, okay? It's just one of those mathematical rules you got to memorize about natural logs and e's. I wasn't great in math, I have to admit. I shouldn't probably admit that, but I think I'm a decent applied epidemiologist. So I think you can understand as much as you need to, and just trust in those things, and use them to make change. Okay, so this is the generalization, value A minus value B. If you have a continuous variable, right? So you're just going to multiply your beta by the difference in those two values if you want a 10-year age difference, a 20-year age difference, et cetera. And then the confidence intervals for binomial regression. Again, it follows that same format, except for it's the exponentiation of beta plus or minus 1.96 times the standard error of beta. So I always have a question. I teach an intermediate methods class in the spring at UIC. And I always have a question on my test about computing by hand a 95% confidence interval. And the students, there's usually about a quarter of them every single year. And in the review, I can head this off, and still at least 25% every year don't get this exponentiation right. They don't exponentiate everything. They don't like add or subtract this all and then exponentiate. So just something to notice. But how often are you going to be calculating these by hand? So it's kind of mean, actually, for me to ask on the test, I think, but you got to kind of remember, where it's coming from anyway. Okay, so for crude log binomial regression, this just shows how the regression equation is directly related to the 2x2 table. So I'll show you that in numbers in a minute for our example, but you can see that P1 is the exponentiation of beta 0 plus beta 1 times x, and P2 is the exponentiation of just beta 0. So the probability of the outcome in our unexposed, as long as we coded it as 0, is going to be the exponentiation of the intercept from the regression equation, okay? And here it's going to be the exponentiation of the intercept plus beta 1 times 1 if we have it coded 1 for yes, for exposed. And this divided by this, P1 divided by P2, or e to the beta 0 plus beta 1x divided by e to the beta 0, is going to reduce to e to the beta 1, which is our relative risk. Okay, so we see how these things relate. So in numbers, we have the same 2x2 table we saw when we were computing the odds ratio, but now how are we calculating the relative risk? Which numbers are in the numerator and in the denominator to calculate the relative risk? Divided by other, right. So the 41% postpartum visit rate for those in MCOA divided by the 56% is just P1 divided by P2, and that's 0.72. So you see now the overestimation of the odds ratio. We were saying they had half the odds of having a postpartum visit in MCOA. Now we're saying they're a quarter less likely, right? It's a huge overestimation. So that's why we're kind of moving away from odds ratios. And especially when we have a health services outcome like this that, well, I think we'd say this is really low, right? But still, it's a high proportionate outcome compared to like things that we're used to studying, like rare diseases like cancer, or where a lot of epi happens, right? Okay, so another way to interpret that, oh wait, I'll go to the model. Yeah, let me go to the model first. So our log binomial regression model, now you notice these estimates are different than the last model we looked at from proc logistic, right? Because now these betas represent the natural log of the probability instead of the natural log of the odds. So our intercept is negative 0.5684, and our beta 1 is 0.3229. And so if we wanted to get the relative risk for MCO versus other, we could put the intercept, the beta 0, plus beta 1 times 1, divided by beta 0 plus beta 1 times 0, and that would be the natural log of the relative risk. We exponentiate that, which it reduces just to beta 1, right? So we're exponentiating beta 1 to get 0.72. It's exactly what we got from the 2 by 2 table, the 41 divided by 56. Sounding good? Okay. So just a note about the SAS code. Since GenMod, so when you do proc GenMod, you're just going to get the beta coefficients unless you do something else. So because proc GenMod is more flexible, it also doesn't know how you want to express your outcome. So it doesn't automatically exponentiate the values like it does in logistic. You automatically get odds ratios out of logistic because it knows that you're going to want to not report the betas being the natural log of the odds, ratio, but you're going to want to report the odds ratio, so it automatically does it for you in SAS. In proc GenMod, you have to do something extra to get this exponentiated and to get these confidence intervals exponentiated so you get a relative risk, so that you don't have to do what we just did and compute it by hand. Okay, and that's called an estimate statement in proc GenMod. Anybody used an estimate statement before? Oh, a few of you, okay, great. It's similar to, you can use in proc logistic, if you want complex contrast, you can use a contrast statement. One of the things that drives me crazy about SAS, I don't know why they used different syntax for those two procedures, but just so you know. So this is an estimate statement, and in the parentheses here, you can put whatever you want, and that's going to come out in the output. So it's helpful to tell yourself, okay, what does this value mean? What am I trying to predict here? And this is the relative risk of exposed versus unexposed. This is general, but if I had my example, I would have had relative risk of getting a postpartum visit, MCOA versus all the others, just to kind of indicate once the output comes out, what was I trying to estimate here? And now I put exposure 1 here. So what you have to write in the estimate statement is actually the simplification of this equation. So you actually have to think through what is going to get me the relative risk itself, okay? So you kind of have to go through that math in your head, a numerator divided by denominator, and then tell SAS, what you're telling SAS here is if this is your exposure, if this was MCOA, you're taking the variable from the right side of the equation here and multiplying that by 1, because you're comparing 1 minus 0, and then after the slash, your option is to exponentiate it. So you're basically, this is telling SAS, take the beta for my exposure variable, whatever variable this should be the same, times 1, and then exponentiate it. And then you'll get a relative risk and a 95% confidence interval from your estimate statement. It'll exponentiate it for you, okay? So these can be a lot more complex, as we'll see, if you have interaction terms, different things like that, but we're starting simple. So there are some drawbacks to the log binomial regression, and I think that's why there's this other option of using logistic to generate relative risks. Sometimes the log binomial model doesn't converge. Mathematically, the properties of the variable aren't quite as nice as logistic, so sometimes the software program is not actually able to solve for the beta coefficients, so it's something to note. Sometimes the confidence intervals are a little narrower than they should be, and sometimes the estimated probabilities from the model may not all be between 0 and 1, which a probability should be between 0 and 1. Sometimes those predicted values are outside of that range, but usually the ratio measures are okay. Like, so if you're not going for the predicted value itself, but a ratio of 2, usually those are all right. But there's some strategies for addressing the first issue about convergence. One of them is just to add, so you have your model statement, we have link equals log, dist equals bind. Add an extra option for intercept equals -4. What this does is gives the software a starting value for the intercept to start solving from. And if you take, I should have done this beforehand, if you take like the natural log of -4, it's some reasonable probability, right? So you're actually starting the software out with a value instead of it starting from nowhere. And sometimes this helps to get it to converge, okay? So it's just a little trick of the trade. And it's not, when you see the results, it's not like your intercept is going to be -4. It's the starting point for the iterative process that it goes through to try to solve for the values that create that straight line, okay? So it'll just start from there, and it'll actually come up with the intercept for your data. Another option is to use Poisson regression and just use a robust standard error to account for the fact that it's using a Poisson error distribution instead of a binomial one. And so this is called, we call it modified Poisson sometimes. And what you do need for this is you need a unique ID number. So if you don't already have an ID number in your data set, you may already. If you don't, though, you can just create one by saying, in the data step, you can say ID equals _n_, and that just gives the observation number as an actual variable. And so then it looks like this. You use a repeated statement here to generate those robust standard errors. And this is where you need to put in that ID. And you use the correlation matrix of independent here. This is to get robust standard errors. This code will look familiar when we start talking about GEE models at the end of the day when we're talking about multi-level models. But this is a way to actually just account for the fact that you've now substituted the Poisson distribution here instead of the binomial one. And what happens, this is more likely to converge with the Poisson distribution, but then you're accounting for the standard error differences between those errors with this extra statement. So another thing that's just kind of handy to keep in your back pocket if you have a log binomial regression that doesn't converge, this is a reasonable approximation, okay? And if you ever need, because I run into issues sometimes with colleagues who are logistic fans, like what are you doing? What is this regression equation? How can you justify using this? You should be using odds ratios and logistic regression, right? Or if you get a peer reviewer at a journal or something like that, there is a handy short little paper called Easy SAS Calculations for risk or prevalence ratios or differences, published in American Journal of Epidemiology, so very reputable source, by Donna Spiegelman, who's kind of an awesome applied statistician out of Harvard. And so this is a nice thing, again, to have in your back pocket and be like, well, see, this like acclaimed statistician from Harvard says it's okay, and it went through peer review, so it's a nice thing to have on hand if you need to cite something in a journal or you're getting resistance to using either log binomial, or modified Poisson. Okay? And there is a folder on Google Drive that we're populating as we go with additional resources. I'm pretty sure I've already posted that one in there. So, okay. Oh, and if you notice here, I ran the data with modified Poisson, and we get the exact same relative risk. And the confidence intervals are a little bit different at the 100th space or 1,000th space, but from a meaningfulness, you might have a statistician going, oh my goodness, it's different. It's not different from our purposes, how we're using it in public health. It's not different. It's not going to give you different conclusions, right? Okay, so any questions before we go on to the additive model? Okay, you guys are either all acing this or you're all confused. I can't tell. Yes?
Going back to that slide you were just on, in the estimate statement, if you list like MCOA, do you sometimes
Oh, you found a mistake. I'm sorry. These are new slides. You did find a mistake. I'm sorry. That should have a 1. Yeah, thank you for being so observant. Oh, why do I keep... Sorry about that. So did everybody see what I did? I added a 1 here. You always have to tell SAS what you want to multiply that beta to. I clearly was editing my slides after I copied and pasted from SAS, because SAS would have given me an error. Sorry, guys. Anything else? Okay, so binomial regression. Again, I'm going to start to sound a little bit like a broken record, but it should make you feel confident that you understand how to handle this right side of the equation, because each time it's the same on the right side. It's just knowing how your outcome variable is transformed and the errors that go with it. So what's nice with binomial, and it really makes the interpretation of the model results very intuitive, is that you're not transforming the outcome variable here. So now we have a dichotomous 1-0 outcome, and we're estimating the probability of the outcome in a straight line relationship with the independent variables. So the link is identity, because we're not transforming, but the distribution is binomial error structure, because we do have a binary variable. You also can do this in GenMod. Notice how the code looks almost exactly the same, except identity link versus log link. So it looks almost exactly the same as log binomial, except the link, right? And that is a very important distinction, because the beta values mean something completely different because of that different link. And so I'm going to point you out, we have some exercises, and I've switched the link on some of them. So you have code and you have output, so be careful and watch to see what the link is, because then you'll know how to interpret the outcome variables. Okay, so the predicted values, what's nice is they're actually the risk or the prevalence, untransformed, equals beta 0 plus beta 1 times value A. So we can actually get the probability of the outcome in the unexposed just by looking at what beta 0 is, and the probability of the outcome in the exposed by adding beta 0 plus beta 1. Okay. And that's what this all says. Now we're subtracting again the risk of one and the risk of the other, and here's where it comes. Our measure of association is a risk difference or a prevalence difference. And as Ashley said yesterday, this is more important from a public health perspective, is this difference, this absolute difference in risk, instead of this ratio of risk that is dependent on the baseline risk of the unexposed, and can look really huge, for a rare outcome, where there's a two times increased risk, but maybe it's a risk of 1% to 2%, right? Maybe it's a risk from 30% to 60%. And on the absolute scale, you would get that distinction, of the magnitude of the absolute difference in risk. So that's why it's nice to have these complementary measures of risk difference and the relative risk. So you have the difference between two risks, one for where x equals value A, 1 versus 0, and that solves to beta 1 times value A minus value B. So the betas associated with the variables are interpreted directly as risk differences. Okay, standard error, or the confidence intervals. Now you don't have that problem with remembering which part of it to exponentiate, because we're not exponentiating, we don't have a transformed outcome variable. And how it relates to the 2x2 table, I'm sure, like I said, that's a broken record, but it's directly related. There's no exponentiation needed. Okay, so here's what it looks like. This is on the top is the results from the contingency table analysis. We have the exact same 2x2 table again, but now I've used the option on the tables statement for risk diff, which gives me a risk difference in addition to the rel risk, option to give me relative risks and odds ratios. And so now you have the 41% minus the 56% equals negative 15, negative 0.1563. If I ran the model, you see that the beta coefficient itself is actually the risk difference and the 95% confidence intervals. So you see how straightforward that is from the model results. So what's the interpretation? I'm sorry, Mike?
Okay, I guess I would interpret it saying that the MCOA's visit rate is 15.6% lower
Yeah, I think it's tricky to distinguish the interpretation between a relative risk, because if you said 15.6% lower, it almost sounds like a relative percent difference. So I think this is hard, though, to really distinguish them. So I typically will say like a 15.6 percentage point lower postpartum visit rate to really make it clear that this is an absolute difference in the rates of the postpartum visit rates, right? But it is tricky to distinguish those. I think that's the hard part about interpreting them side by side, because we often say, like for the 0.72 risk ratio, we might say 28% reduced, prevalence, or reduced postpartum visit rate, or something like that, where it's a relative percent change. This is on the absolute scale. So we're saying it's a 15% percentage point difference, or for every 100 women, 15 fewer women in MCOA received a postpartum visit than those in other MCOs. It's another way of saying it, to really drive home that it's an absolute difference. It's hard, though, I think. Okay. Yeah, I don't actually have that one written down, but for every 100 women, 15 fewer women served by MCOA received a postpartum visit compared to women served by other MCOs. Does that make sense? Or 16 if you want to round up, Although I always think it's funny to round up when you're talking about like people. I guess it's still a percentage, so it's okay. All right, so here's some resources. I have the same Enrich webinar. I highly recommend it, that Ashley was talking about. I have, does anybody use the UCLA? Yes. Oh, is that site amazing? I love it. I use it all the time because it shows the code and the output, and then it annotates the output. Like what do all these pieces of the output mean? So I just have a link here for a log binomial example from that. If how I said it didn't make sense, maybe how they said it will, because they're really good at it. But for any of you who don't know this, if you ever Google UCLA ATS, like there's a lot of different, it's SPSS, Stata, SAS code, a lot of useful resources there. Also, here's the macro where you can produce the relative risks and risk differences from Logistic in SAS. There's some limitations of this, so you could kind of look into the documentation, and that's why I'm not teaching it yet in SAS. But we'll, when we share the code document, we'll share how to do it in Stata, because it's quite simple to produce the marginals from logistic regression to actually compute correct relative risks and risk differences from that. And then here's just from the Epidemiology Matters textbook. They have a website that goes with it that talks about relative risk regression. Okay, so now we're going to talk about dummy variables. How many of you have used dummy variables? Oh, okay, so quite a bit of you. So this is kind of a review. I think it's so powerful to know about dummy variables because I see so many people who don't know about them and they feel like they need to dichotomize everything. And most stuff, a lot of stuff anyway, isn't just a straight dichotomy. So we've been looking at MCOA versus all the other MCOs. Well, what about those other MCOs? Why did we group them all together? And it really was just so I could show you the basics in 2x2 tables. So there is actually 4 fake MCOs in these data. They're actual real Medicaid data, but I didn't have MCOs, so I made that variable up, just so you know. So the postpartum visit rates are truly that low in the Medicaid data I was using, but I made up the variable for MCO. But there's 4 in this kind of fake home state. And so we want to actually be able to estimate relative risk for each of them, right? Not just MCOA. So the idea here is to create, another example is if you had race ethnicity. We very infrequently have just 2 categories for race ethnicity. What if you have 3 and you want to model African American, Hispanic, and white? You can see that the null hypothesis would be that the natural log of the risk of the outcome is the same for all of those 3 race ethnicity categories. So if you put race ethnicity in a model, just like this, it would try, and you have it coded as 1, 2, 3, you know, for African American, Hispanic, and white. It's going to try to draw a straight line, like treat it like an ordinal variable, right? And this is not an ordinal variable, it's a nominal variable. It doesn't make sense for every unit change in race ethnicity, right? That beta coefficient would not make sense at all. So that's why I have a big X through this, because you couldn't model it like that. So we need to trick the modeling procedure, and we do that by creating dummy or indicator variables. I'm going to kind of go through this quickly since most of you seem to know this. But what dummy variables look like, if this is our original variable, for race ethnicity coded 1, 2, 3, this is the matrix with 2 dummy variables. So dummy variables are always going to be k minus 1. If you have 3 categories, you'll have 2 dummy variables. And so we have a dummy variable here for African American and for Hispanic, and you have to choose a common reference group. So this is the one thing, you are choosing a common reference group for each to compare each of them to. And so we chose here white as our common reference group. So on both dummy variables, they're going to have a value of 0. For the African American, it's going to be 1 versus everybody else is 0. And for Hispanic, they're going to have a value of 1 and everybody else is 0. Okay? So it's not that it's just, I wish I could cover this one up. It's not that it's just 1 and 0, Hispanic versus white, because white is our common reference group. Everybody else has to be coded 0 in order for then the combination of these 2 dummy variables in the equation will create the common reference group of white. This is how you would code dummy variables. So it's if your race ethnicity equals 1, then your African American variable equals 1, else everybody else, as long as you don't have a missing race ethnicity variable. So this is key. You don't want to code everybody else with missing race into your comparison group, right? Then it's 0. So this is how you would actually code it. But you don't really need to do this in SAS. You should understand how this is working, but you could just use your race ethnicity variable in a model statement here, but here's where that class statement comes in that I talked about before. And here you can use a referent to define your common referent category. Here again, I have, it's a numeric variable for race ethnicity 1, 2, 3, but I have them formatted. So I can choose a reference group of white, and that's my formatted value that I put in quotes. I want to use the parameter equals reference, parameterization equals reference coding here. What that means is, by default, definitely in Logistic, and I think in GenMod too, SAS codes dummy variables as 1 and -1 instead of 1 and 0. So if you say you want reference cell, I think that's indicator coding or something like that. If you want reference cell coding, though, for 1s and 0s, you have to put this option on, param equals ref, okay? So now the model statement that I crossed out before is okay, because what SAS is going to do when this variable is in the class statement is create dummy variables on the fly to use in that procedure. It's not actually going to create these dummy variables in your data set, but on the fly it's going to create dummy variables, and you'll see that you get estimates then for African American versus white and for Hispanic versus white. You'll get 2 beta coefficients associated with that one variable in the model, okay? And so we're going to go to the exercise next, which has actually our regression equation now with all the MCOs in it. So it's still a simple, postpartum visit equals MCO, but now you have dummy variables for the different MCOs, and you can estimate relative risks for each of them versus the common reference group. And in this case, I have A, B, C, D for the MCOs, and MCOD I chose as the reference category because it had the highest postpartum visit rate, okay? So if you look in your folder, there is an exercise. It'll be under Tuesday. If you go in the exercise folders, there's a check-in exercise, and there's several different models on there. If you want to just start with model 1A and answer the questions under that, I'll give you about 5 minutes or so for that. Okay, any questions before we go into that? Okay, I'll be circulating if you do have questions for me. Windows P, okay, I never knew that before, okay, excellent. Okay, perfect, thank you.
So now it's on duplicate, and if you want to go back,
Okay.
Windows P, just cycle through.
Okay, sounds good. Do you remember by any chance what the internet code is? Okay, I'll ask Maureen. That's okay. Thank you. Okay, you may not have all of them done, but I'm going to walk through a little bit some of the output. And I will post answer keys for all of these. I will not post answer keys for the conceptual model from yesterday because there's no right answer to that. That's kind of like, you're reasoning through and you're thinking through and stuff, but some of these have nice right answers, which is always, I feel like EPIs always want to know, is it right or is it wrong? That's just our nature, so there are a few times when you'll get that satisfaction of knowing whether your answer is right or wrong. We usually don't have that in our work though, right? Okay, so this model, first of all, as I headed you off, you want to notice that the link is a log, right? So we're using a log binomial model here to predict what measure of association? Risk ratio, right? And so we use a class statement for MCO now. Now we have a variable. This isn't MCOA anymore. This is just MCO. There are 4 categories. How many dummy variables are there going to be? 3, right? It's always k minus 1. And so here it shows you, I think this is one of the most important things to look at in your output. I didn't put all the SAS output on here, just select pieces of it or whatever. But one of the most important things to look for is this design matrix for the class level variables. This tells you exactly how SAS created your dummy variables. So I said MCO here, and I didn't have a referent group, and that's because it'll, by default, take the last one, and that's what I wanted, okay? You can use ref equals first here. You could do in parentheses MCOC if we wanted MCOC to be our referent group, right? I didn't have to do any of that here because by default it's going to be the last one, and I wanted D to be the referent group. But I have the param equals ref, so you see it's created 1s and 0s instead of 1s and negative 1s. And so now we have 3 dummy variables, one comparing MCO A to D, B to D, and C to D, okay? You see how they're coded. That's very important in interpreting the results. Then you get the number of women in your in the group that got a postpartum visit, the number of women who didn't, and this is also very key. This shows me that GenMod is modeling the probability the postpartum visit equals, and it's my formatted value, postpartum visit, which underlying that is the value of 1. Now, if I didn't have this formatted and I didn't use a descending statement, this would have said it's modeling the probability that postpartum visit equals no. And like Ashley said yesterday, they're not the inverse of each other for a relative risk like they are for an odds ratio. So you have to decide whether you want to model getting a postpartum visit or not getting a postpartum visit. And so I made a decision to model getting a postpartum visit because, and it's a positive outcome. It's interesting, right? We're always thinking about like disease being like the negative outcome, relative risks above 1, right? But for a health services outcome like this, I think it makes sense sometimes to model as getting it. And what are the factors that are associated with getting it or having a lower rate, right? You could have made the decision to model not getting a postpartum visit. But then all of your interpretations, you end up in double negatives, you end up, and it's a lot clearer to people to say it's a lower postpartum visit rate, to actually be modeling the postpartum visit rate instead of the lack thereof. Does that make sense? Okay. So anyway, that's important to see though, because you could be getting estimates on opposite sides of the null and not really understand why, and you might be modeling it the wrong way. Okay, so now we have a beta 0 and beta 1, 2, and 3, because this MCO variable we created 3 dummy variables out of it. And I asked you to report the appropriate measure or measures of association in 95% confidence intervals from the model for the unadjusted relationship between MCO membership and postpartum visit receipts. So I wanted you to get here that we needed 3 measures of association, 3 risk ratios, and how to calculate each one of those. And so how would you calculate for MCOB versus MCOD? Just as one example. B versus D. Sorry, guys. I need to bring my mouse up here. I'm terrible at these. The exponentiation of negative 0.096, which equals the exponentiation of negative 0.096, which equals, what did you say, 0.91? Okay. So those in MCOB have a 9% lower postpartum visit rate, 9% lower relative to MCOD. You could also exponentiate these two walled confidence limits. You can exponentiate each of these to get a confidence interval around that. I don't have offhand what it is, but we see that they're both negative, so we know that it won't include the null value. Right? Okay, so that's pretty clear to you, right? And if you wanted to, compare B to C, you would, exponentiate this minus this, right? If you plugged in the equation, it would reduce to, one minus the other. So you can really be flexible. If you understand what the regression equation means, you can be flexible about the contrasts you want to make if you decide I want to change my reference group. All right. So the second question was about what's the estimated postpartum visit rate for women served by MCOB. And here, what do we have to do? Right. For the predicted value, which is the rate, the postpartum visit rate in MCOB, we have to take the exponentiation of the intercept plus the beta, because now it's just the numerator of that risk ratio that we just calculated, right? It's just the postpartum visit rate among MCOB, and the intercept is it's 0.642. So we'd exponentiate 0.642 plus negative 0.096. Did anybody get that value? I don't have my answer key with me, sorry. Anybody? Right, something's wrong. Can't be 1.73, right? All right, I will figure that out and get back to you guys, because that can't be right. That's not a proportion. Now it should be a value between 0 and 1. So I'll figure that out and get back to you guys. And I'll post the answer key for that. But it should be the exponentiation of the intercept plus the beta for MCOB. So, okay.
So did you interpret that as 0.9 percentage, wait, sorry, 9 percentage points lower than
Right.
MCOB?
Right. So you can, for question 1A, if the relative risk is 0.91, it's either that those served by MCOB have a 0.9 times the postpartum visit rate as MCOD, but it's a lot easier to talk about it as a relative percent difference, which would be have a 9% lower postpartum visit rate than D. Those served by B have a 9% lower postpartum visit rate than those served by D. Does that make sense?
Yeah, I guess I'm really confused because how did you figure it's lower? Is it because of the
Because it's below 1. So 1 is our null value. All right, so I'm actually going to go straight to model 1B and talk through this a little bit. In the slides, you could go back to the slides later, but I think you guys have probably a pretty good sense of adjustment in models. So for the sake of time, I'm just going to walk through what this model is showing and then have you do the exercise. You'll see the first part of the question of the exercise. The second part, I had kind of a squirrel moment. I must have started the question and gotten distracted, which happens a lot. You know, an email came in or something like that, so it doesn't really say anything. So you don't have to do a second question. So sorry about that. But so model 1B is the same model, the same base model. So it's a postpartum visit equals MCO, and now we're adding some of our covariates to the model. So remember from the data dictionary yesterday, we have other variables. These are our third variables. So if we decided for each of them, we're going to adjust for them, and I'll show you an example later with an interaction term, because I know we hypothesized some effect modification. There wasn't a lot going on empirically, I will say, but we'll look at a model with interaction terms. But here we're just adjusting for these factors. So now we have age in 4 categories. We have race, ethnicity in 4 categories. We have poverty status for the neighborhood in 4 categories. And remember, we have that mental health risk. We have having a mental health diagnosis. So here's our covariates. We've thrown them all in the model here. So now it's an adjusted model. So now if we wanted to estimate the effect of being an MCOA after controlling for all those other variables. So now remember back to the counterfactual model and exchangeability. Right? We're controlling for these other variables because we think they're confounding the relationship between MCO and having a postpartum visit. We're controlling for them to try to make our MCO A, B, C, and D exchangeable with each other, trying to make them similar, right? So here this is the empirical model for the adjusted. And so now we want to estimate what is the relative risk of being an MCO A versus D, B versus D, C versus D, after adjusting for all these other factors, right? And so notice a lot of these variables, like I said, we have very few actual dichotomous variables, I feel like, sometimes in MCH. We wanted to model here age in 4 categories, race, ethnicity in 4 categories. So you see I put all of these in the class statement as well so that they're modeled appropriately as dummy variables. So you're going to have a lot of actual beta coefficients from this model, even though you're only seeing 5 variables in the model statement. Now, mental risk, since this is a 1-0 dichotomous variable, I didn't put it in the class statement. You could. It would flip the interpretation. You would just have to see that. But I typically, with my 1-0 variables, just leave them as is in the model statement. And so now we have a log binomial regression again. So now we're going to be, how are we going to assess from the results of this model whether these factors are confounding the relationship between MCO and postpartum visit? Once we get the results of the model, how would we assess for confounding jointly by this set of 4 third variables? Oh, sorry about that.
What are the changes in the data values from the original model?
Right, so you're going to look at the unadjusted estimates for the relative risks for MCOA from the first model that we looked at, and then look after adjusting. So when we exponentiate those betas for the MCOs, now from the second model, those beta estimates themselves are going to be adjusted for everything else in the model. So when we exponentiate them, we're going to get an adjusted relative risk, and we can compare the crude to the adjusted for a conventional 10% difference, right? We usually use like 10% to look for confounding. Okay, so try that out and let me know if you think that those factors are jointly confounding that relationship. Okay. Okay, so what are you finding? a little tricky because you have to compare the 10% differences for all the different levels of MCO, right? You think there's confounding? Yes? Okay. So what'd you get for MCOA unadjusted? Was what? Say it again, 0.7. And MCOA adjusted? Yeah, 735, okay. MCOB unadjusted was 0.91, right? Adjusted? Sorry. Say it one more time. Okay. Okay, so those are almost exactly the same, right? And how about MCOC? So not very different than MCOD, right? MCOC and D are very similar. How about adjusted? Okay, so you had said you thought there was confounding. Why? Everybody's like, I didn't say that. Yeah, no, that's okay. Yeah. If we were calculating a 10% difference, it would have to be 0.72 or lower, right? So, it's convention. 10% is convention. And also, when we're talking about model selection later, we'll talk about whether sometimes it makes sense to control for things, even if they're empirically not acting as confounders, because either everyone and their brother has, or everyone and their sister has done it in the literature, and you want comparable results. So there's these conceptual confounders that we think of as things that should be in the model anyway. Also, when you have a sample size this large, we're looking at like 50,000 observations from claims. Sometimes you want to go in with your conceptual model and test your conceptual model, and really there's no need for parsimony. So you might want to adjust for these things anyway, even though it's not reaching that 10% perspective. And that's some of the art of epi, thinking through what makes sense. If this is a conceptual confounder, do we want to keep in the model no matter what? And I'm kind of giving away some of my discussion later about model selection. Okay, so I think we're going to take a little bit of a break now, and we'll come back and start out with the slides from that start on Wednesday morning at 8:30 in your Google Drive, because the rest of the slides from the other thing were just about adjustment, and I think you guys get that, so we'll move on to the next assignment. But we'll have about a 15-minute break here, and we'll come back at 10:15. Okay, thanks.